Good afternoon, dear audience. First of all, I would like to welcome to session 12 of Pvcon 2020. I would like to also thank to the organizing and scientific committee of this special event. In this session, there is 4 speakers who will focus on the topic of PV module performance and reliability. Before I invite the first speaker, I want to give a short introduction about her. The first speaker will be Beyza Durusoy. She has completed her bachelor's and master's studies in the physics department at Middle East Technical University. During her studies, she focused on the outdoor performance of PV modules. She is now a PhD candidate in the micro and nanotechnology program and supervised by Professor Rash Turan and Professor Bülent Akınoğlu in Middle East Technical University. Her presentation topic is technical potential of residential rooftop solar photovoltaic for Ankara. This is a preliminary study. So welcome, Ms. Drusoy. So you may start your presentation.
I also previously sent the recording. Maybe you can start it.
Okay.
Hey everyone, my name is Beyza Dursoy. I'm a PhD candidate in Micro and Nanotechnology Department at METÜ. Today I'm going to present you a study about the technical potential of residential rooftop solar PV for Ankara. And this is a preliminary study that we have conducted with Ceren Kutlu and Professor Bülent Akınoğlu. As you all know, the energy problem is a global concern right now. With the growing population, the energy consumption increases significantly. Cities are responsible for over 2/3 of the total energy consumption, and the buildings cover half of that ratio. For these reasons, many countries take steps to make sure that the energy demand is met. Currently, 250 cities, including London, Los Angeles, Tokyo, and Paris, they all have 100% renewable energy targets, and these metropolitans aim at zero emissions in new buildings by 2030 and in the existing ones by 2050. And when we look at the situation in Turkey, we see that it has a dependency ratio of 73.8% for overall energy and 51.11% for electricity. Emphasizing more decentralized solutions as citywide and municipality-based policies would provide more effective and faster results to reach renewable energy targets. Before going into the details of our study, I would like to mention some rooftop PV potential studies. As I said before, it is getting more common to use renewables, and there are some studies explicitly focusing on rooftop PV potential, such as in Spain, Italy, Germany, Israel, India, and Japan. Besides, some cities have strict regulations, such as in Dezhou, Vienna, and Freiburg. For example, in Dezhou, China, almost every roof is covered in solar panels. In Vienna, it is obligatory to use rooftop PV in new buildings. As you can see, the little picture on the left, it is taken in Freiburg, Germany. You can see that every roof has PV modules, and for this reason, that south part of the city is called the Sun City. After seeing all the city-based studies and regulations, we wanted to analyze the rooftop PV potential of Ankara according to building and module types. There are 2 studies about the PV potential in Turkey, and we wanted to contribute a city-based potential study, considering the fact that Ankara has a higher solar irradiation yield and more public buildings than most of the European cities. For these reasons, we want to propose an accurate methodology which is reliable, free, open-sourced, and most importantly, applicable to every type of roof. In this study, we have used 3 types of residential buildings: pitched roof apartments, flat roof apartments, and detached houses. Since there are no specific data for roof areas, we have revised the trick data for residentials. We have calculated the floor base area of buildings by dividing the total building area to floor numbers. By doing so, we have assumed that floor base areas are equal to the roof areas. As a side note, we have only included buildings that are built after 2000 to make sure that we do not have any roof stability problems. Let's have a closer look at our samples. The buildings are selected randomly from different parts of the city Ankara. Among these samples, 12 of them are pitched roof high residential buildings, 2 of them are flat roof apartments, and 3 of them are detached houses. And from the table you can see the rooftop type, number of floors, number of dwellings, and the roof area. For all samples, monocrystalline silicon, polycrystalline silicon, and bifacial modules are settled. For pitched roofs, modules are installed as flush mount, and the optimum tilt angle is selected as 32 degrees for Ankara. In order to reduce shading effects, we have calculated the row spacing by considering either the roof area or the module type. Now, to make it more visual, I'd like to show you some pictures. Sample 1 is a high residential building roof, and sample 15 is a detached house. And you can see 3 different applications. First one is mono C application, second one is poly C application, and the last we have the bifacial application. The usual settlement for rooftop PV is that it's free of modules in the north side. Although this doesn't create too much difference in 4-segmented roofs, it creates a significant difference for bifacial PV in 2-segmented roofs. And we have used helioscope tool for these simulations. Here we can have a look at one of the applications. It is for monocrystalline silicon PV modules. Number of PV modules and the annual energy yield values came from the helioscope application results. By multiplication of number of modules and the module area, we have found the usable area, and then the usable area ratio is found by the division of total roof area measured by Google Earth. After finding the suitable area constants, we reapply these constants to the total roof area with the help of tweak data. And what do we mean by that? The suitable area constants, which found in table 4, multiplied with the total floor area and settleable module number in this area is found. Then the total energy is calculated for each module, since the yield is highly dependent on spacing, module area, and module types. Let me move on to the results of this study. You can see the results for the 3 different types of module application to 3 types of residential buildings. For pitched and flat roofs, monocrystalline silicon PV modules perform the best, and for the detached houses, it's the bifacial PV modules. As I said before, main difference occurs for bifacial PV in detached houses for 2-segmented roofs. But these results do not necessarily mean that one type of module is superior than the others. It shows how important is the module size and row spacing in limited roof area. To conclude, we have performed an analysis to observe the rooftop solar potential in Ankara. Results show that the energy yield of the PV system is highly dependent on the building and its roof type. If the row spacing arrangement is done to the buildings individually, the potential would be higher due to the better settlement for shadings. Moreover, 2,500 buildings are adding to Ankara every year, so we can say that the potential keeps increasing. For the future studies, we would like to complete this study in a much bigger scale, including more buildings for a longer period of time. Besides, a feasibility analysis will also be conducted to get a more realistic view of the rooftop solar potential. Thank you for listening. If you want further details, you can have a look at our reference list, and if you have any questions, we will be happy to answer them.
Thank you very much for your nice presentation.
Thank you.
I'd like to ask, is there any question? I don't see any question on the message part, but I want to ask one question. when you share the results of your study, you have mentioned about the megawatt hour production. So this is the energy production. What about the installed capacity of the PV systems according to your calculation?
Mhm. That was only one application of the. That was only the results of one application, one
Or
type of.
are they right? I mean, normally when we mention about this type of studies, we share first the installed capacity of the systems, then we can also share the predicted energy production. But I have just noticed you only share megawatt hour. Is it megawatt hour or just megawatt, the installed capacity?
No, it's megawatt hour, it's annual energy yield, and it is
Okay.
simulated results, so it's a theoretical study, we
Prediction.
can say. Yeah, it's a prediction. We estimated it will be a megawatt hour for annual energy production.
Okay, thank you very much. I think
Thank
there
you.
isn't any other questions, so
Okay.
I would like to pass the other presentation. The second speaker will be Nahide Özben Kaya from Şişecam. I'd like to also give a short introduction about her. She graduated from Metallurgy and Materials Engineering Department. She completed her master degree on glass technology. She's currently working as a researcher at Şişecam, which is a leader company in the glass sector in Turkey. Her presentation topic is potential utilization of thin patterned glass in photovoltaic systems through chemical tempering. So I would like to give the talk to Ms. Nadide Özben Kaya.
Hello everyone, I am Nahide Özben. I am working at Şişecam Science, Technology and Design Center, and also I am PhD student at Yıldız Technical University. My presentation will include the following main headings. I will briefly talk about the relationship between the photovoltaic system and the cover glass used in the systems, and briefly explain the chemical tamping process applied to the cover glass that we have experimentally studied for use in photovoltaic systems. After that, I will share our experimental studies on that topic. Finally, I will finish my presentation with results and conclusions. The amount of produced energy in photovoltaic systems significantly depends on the properties of cover glass. It's always desired that the sun rays passing through the cover glass reach to the cell with the least possible loss. To get higher efficiency from photovoltaic systems, the studies are concentrated on different strategies, such as reducing the amount of iron oxide in the glass batch, applying multilayer coatings, for example, anti-reflective coatings, patterning the glass surface. The patterned glass surface allows more light transmission than the float glass surface. Patterned glasses that direct the light coming to the surface of the glass and allow it to return inside, reduce reflection losses. Reducing the glass thickness, thinned glass used in photovoltaic modules has become one of the highlights of the glass industry. It has been determined by previous studies that the thinner glass, the higher the permeability of the glass. However, as the glass thickness decreases, the strength values also decrease. At this point, chemical tamping process is used to increase the strength of thinned glass. Let's start with chemical tamping process. The process needs relatively high temperature. It's performed below the glass transition temperature. Potassium nitrate is most widely used salt in this process. It's an ion exchange process, exchange of smaller alkali ions like sodium in the glass matrix and larger alkali ions like potassium in the molten salt beds. Ion exchange realized in alkali-containing glasses. By this ion exchange reaction, compression layer is formed on the surface, thus glass is strength. The usage area of chemical tempered glasses increasing day by day. Chemical tempered glasses can be used in automotive, luxury vehicles such as yacht classes, display technologies, and glasswares. There are many parameters affecting chemical tampering process, like surface conditions, glass thickness, glass compositions, reaction temperature, reaction time, wet conditions, and salt tip. And in our study, we focus on glass surface conditions and glass thickness. In our project, we have completed our research on two main topics. We have studied with 2 mm soda-lime silicate glass composition. First, we examined the chemical tampering behavior of patterned glass and compared it with the float glass. Then, we examined the influence of glass thickness on chemical tampering process. Finally, the resistance of chemical tempered patterned glasses against atmospheric conditions was examined. Let's look at our experimental studies briefly. In study where we examined the chemical tampering behavior of patterned low iron glass, we cut our glass samples in certain size and then cleaned with the demineralized water and isopropyl alcohol in ultrasonic beds. We carried out chemical tampering process at 450 degrees for 4 hours. Time and temperature values were selected in the accordance with the information obtained from the literature and the experimental studies we have done before. Then the results were compared with the results obtained in study with float glass. In the second part, where we will examine the effect of thickness, we will compare 2 and 3.2 mm patterned glasses in terms of chemical tampering behavior. In the last part, the resistance of chemically tempered patterned glasses to atmospheric conditions such as humidity, salt, acid, and abrasion was examined. These are our characterization studies. In order to determine the weight difference and mass average diffusion coefficient, the samples are weighed before and after chemical tampering process. SEM EDS light scan analysis was performed to measure the potassium diffusion depth depending on potassium concentration. Optical transmittance and haze measurements were performed before and after chemical tampering process. White light interferometer was used for determine the surface roughness. Fracture load was determined by using ring test. Let's continue with the first part. This slide shows that the patterned and float glasses which were chemically tempered at 450 degrees for 4 hours, and the weight difference before and after chemical tampering process, the diffusion coefficients and depth of potassium ions in the glass after chemical tampering process. And it's seen that the highest white difference value, the highest diffusion coefficient values, and the highest potassium diffusion depth values were obtained for the 2 mm float glass sample. When the surface roughness values of patterned and float glass were compared, it was seen that the surface roughness values increased with the application of patterned on the glass surface. And there was no significant change in the surface roughness values with the chemical tampering process applied to patterned and float glasses. In this slide, ring test results and variable modulus are given. According to the results after a chemical tampering process, the fracture load value of the SGC pattern sample increased up to 3 times, while the fracture load values of the float glass sample increased up to 3.7 times. Considering the amount of the bending of the glasses during the ring test, it was determined that the increase in the bending values of the patterned glass was lower compared to the float glass. The variable modulus of the SGC pattern and float glass samples achieved from 7.8 degrees to 22 degrees after chemical tempering process. As a result, when chemical tempering process is applied to patterned and flawed glasses, it has been determined that the fracture load values are more reliable than the adhesive glass. When the optical transmittance and haze values before and after chemical tempering were examined, there was no significant difference between the samples. It has been observed that the decrease in the iron content in the glass composition and the application of patterns on the glass surface increased the optical transmittance values. In this part, 2 and 3.2 millimeter patterned glasses were compared in terms of the weight differences before and after chemical tempering, the diffusion coefficients, and depth of potassium ions into the glass. In the first graph, it was shown that the weight difference values for the 3.2 millimeter patterned glass samples after chemical tempering were higher than the 2 millimeter patterned glass sample. It was observed that there was no significant change in diffusion coefficient values. Potassium diffusion depth of 3.2 millimeter thick patterned glass was found to be slightly higher than 2 millimeter patterned glass. When the optical transmittance haze and values of the samples before and after chemical tempering were examined, there was no significant difference in the transmittance values of the glass samples. When the haze values before and after chemical tempering are examined, while the haze values before chemical tempering were similar for both thickness, it was observed that there was no decrease in the haze values after chemical tempering. This decrease is greater in glass with a thickness of 3.2 millimeter. When we look at the surface roughness values, while surface roughness values don't change with the chemical tempering process, roughness values increase with the increasing glass thickness. It has been observed that the fracture load values increase with the increasing thickness of the sample. According to results, after chemical tempering process, the fracture load value of the 2 millimeter pattern sample increased up to 3 times, while the fracture load values of the 3.2 millimeter pattern sample increased up to 4.4 times. When we look the bending values which are obtained during ring-o-ring test, it was determined that the bending values of 2 millimeter glass after chemical tempering have a higher compared to 3.2 millimeter glass. With the chemical tempering process, the Weibull modulus of both 2 millimeter and 3.2 millimeter thick samples increased to 22 degrees. As a result, it has been determined that when chemical tempering is applied to glasses of different thicknesses, glass became mechanically more reliable. Let's continue with the last part. In this part, the resistance of chemically tempered patterned glasses to atmospheric conditions such as humidity, salt, acid, and abrasion was examined. These are our test parameters according to standards. In this slide, ring-o-ring test results values are given, although a slight decrease was observed in the fracture load values after the atmospheric condition test. It was determined that no significant change was observed because these values were within the standard deviation values. Weibull diagrams were drawn using the values obtained from the ring-o-ring test. It was observed that the Weibull modulus increased after chemical tempering. It seemed that the Weibull modulus of chemical tempered glass samples decreases after the test with atmospheric conditions. As a result, it has been determined that the chemical tempered glasses are more reliable than as-received class in terms of resistance to atmospheric conditions. When the optical transmittance and haze values before and after chemical tampering were examined, no significant difference were observed in the transmittance values of the glass samples. When we look at the surface roughness values, it has been observed that the atmospheric conditions don't significantly change the surface roughness of the chemically tempered glasses. And when all the results are evaluated, it has been proven that low iron pattern thin glasses instead of float glass can be used as a cover glass, obtaining a higher efficiency in the photovoltaic systems without any loss of mechanical properties. Thank you for listening.
Thank you very much for your presentation. There is one question from Professor Şener Oktik about the unit of the axis. Nayda Hanım, you see, I think, the question. Could you please answer it?
Okay, I hear you. Which axis? I don't know.
It is written in the chat part, but I can read the question. The unit of the axis is not read properly. Is the weight differences per centimeter square?
Yeah, that's a centimeter square slash seconds.
Okay. Okay, sorry, then only the one I see the question, sorry. Okay, you answered already the questions. So thank you very much. So I want to ask, is there another question? I think there isn't. I would like to thank again, and I want to pass the third speaker to Fateme Mostofi. I want to introduce her again. She's PhD student in construction management of Karadeniz Technical University. She has previously attended Heriot-Watt University, Dubai campus, where she got first class honor in civil engineering, and she developed a career as part-time civil engineering lecturer. Simultaneously, she has worked as project manager, business development in SEMT Limited company. She worked on wide range of projects there. And right now, she truly enjoys gaining new experience among the dynamic research environment of Karadeniz Technical University. She hopes to find a way to reduce building energy, retrofitting costs using less data-intensive machine learning tools. So I want to invite Ms. Mostofi for her speech. Yeah.
Good afternoon.
Good afternoon, welcome.
Thank you. Hello everyone, this is Fatema Mostofi. I'm a construction management PhD student in Karadeniz Technical University. This is my first time being a conference in Turkey. I'm quite excited about it. Today we are going to talk about the structural performance of the roof of existing building under the load of the PV panels, additional load of the PV panels. First, we talk about the energy on today's climate context, and then we define the problem after using a case study to better illustrate the problem. Then we perform the finite element analysis over this case study of a building to see if the roof of this existing building can carry this additional load of PV panels. And at the end, we shortly reflect on the result. As you know, the growth in population, along with the increase in fossil fuel consumption, results in larger volume of greenhouse gas emissions, which in turn result in changes in our surrounding environment. We are having the hotter summer days, colder winter days, which requires more energy to be used for these extreme seasonal conditions. This brings us back to use more fossil fuel consumption. So in order to break this negative loop, we need to use this renewable energy instead of these fossil fuels. Fortunately, during the past decades, there have been a number of good technologies which are converting these renewable energies into the heat or electricity. One of these technologies, which its result fortunately is decreasing over the past few years, is the photovoltaic panels. These photovoltaic panels are able to directly convert this solar photons into the electricity. And they have a very good potential to be used in a wider context. Let's look at the Turkey's map of photovoltaic power potential. As you can see, Turkey has a very good photovoltaic power potential. When we are saying very good, we can say we are comparing it with the map of Europe here. As you can see, most of the Europe is located in the light here, yellow, but they are still using these photovoltaic panels. So here in Turkey, we have cities mostly in the light orange or in the dark orange area. We also have cities even in the purple area. So Turkey have a very good photovoltaic potential, and it remains to the engineer to fulfill this, actually engineers and designers, to fulfill this photovoltaic potential by wider application of these photovoltaic panels. One of the areas we can use these photovoltaic panels is on the top rooftop of the existing building or the buildings. As for the new buildings, we don't have any problem, as we can easily integrate these PV panels in the design of these new buildings. But for the existing building, we are facing the challenge. When we want to install these PV panels on the roof of these existing buildings, we don't know if these already aged structures can carry this additional load of PV panels, and that stops many to use these PV panels over the aged buildings. So at one side, we have these PV panel loads, which we need to see if the building can carry it. And at the other side, we have the aged structure. We have to just evaluate the performance of the existing performance of the aged structure at its existing condition. And that's why we are using a case study to address this question. We do the finite element analysis over this case study, and we have narrowed down our study to only the flat roof. So our focus is on the flat roof of existing building under the PV panel load. And then we discuss the layout to fulfill this purpose. For the PV panel types, we have selected two typical PV panels which can be found easily in Turkey. Monofacial PV panels and bifacial PV panels, which, as their name is suggesting, one of them is only absorbing the solar photons from one side, and the other one, the bifacial PV panels, can absorb the solar photons in both sides, which offers much higher efficiency. And that's why its thickness is slightly more than, is 4 millimeter more than the monofacial PV panels. So though they are almost the same length, 2 meter length and 1 meter width, but the imposed load coming from this bifacial PV panels is slightly more than, actually slightly in terms of a square meter per square meter, more than the monofacial PV panels. That's why we consider the load of bifacial PV panel over our case study. In addition to the self-weight of this PV panel, we have the self-weight of the installation equipment coming along these PV panels, the racks, flashes. We have to consider the weight of this installation equipment. In addition, we consider the load combination of this self-weight plus the snow load, which is we need to consider that for sure. There is no way out of it. And we also considering the typical wind load as part of our calculation or analysis, but we are considering only the typical wind load, as the racks are coming with the PV panels, usually are pre-designed in order to withstand the normal wind load. But for this study, we are not considering the extreme wind load condition. This requires additional study in this topic. So this is our case study. This is the 30 years old factory. It consists of two different types of steel roofs sitting over many numbers of reinforced concrete columns. That's why we call it as a conventional building. And they still are ST52 profile. Let me show you the steel profiles here. We have type A, which are D60, 60 millimeter in diameter and 32 millimeter thickness. Similarly, we have type D18. Type B is 80 millimeter in diameter, 32 millimeter thickness. And here is the profile of our roof, which is this is steel profile type A and B, and we have the roofing on top of this. And what we have done, we have selected a portion of this roof to perform the finite element analysis over this. This selection allows us to generalize the analysis result for further replication for other types of the other part of larger parts of this plan, and also we can use this for the other conventional buildings having this similar nature, sharing the similar nature. And of course, we save the calculation cost. We can have better calculation cost here. So here is our structural model. We have modeled it using SAP 2000. After performing the finite element modeling, what we have done, we have first consider the existing condition of the building under the normal loading condition which the building should carry. So we have added the self-weight of the building, HVAC loading, snow, and the wind loading to our final element models as defined here. Then we have defined three loading patterns. Why we have done that? We wanted to see if the roof of the building can be reinforced only using the minor reinforcement on some of the critical parts, or we need to do some major operations there before installing the PV panels. We have three loading scenarios as shown here. First, we just partially load our panels here, here, and here. And in the second loading scenario, we leave the middle panel empty, two middle panels empty, and only loading the roof at the side. And the third loading scenario is our most critical scenario, which is our main focus, and we fully load our roof, and we make the full panels over the roof. So this is our existing condition of the buildings. This is the aged building simulation without the load of the PV panels. And what we have done, we have recorded the deflection 3.43 centimeter, and we have seen that under the dead load plus this is the ventilation loading, which is a very important consideration here. We have to consider the ventilation for loading for all types of similar structure. 150 elements have failed under this condition, and when we added the snow load in our load combination, we have seen that almost double number of elements failed. 315 elements failed under the stress applied by this conventional loading without the PV panel load actually. And we have also observed the double amount of deflection here, 7.18 centimeter of deflection. And our central elements dividing this A and B sections are our most critical elements here. Then we have applied our load patterns of the PV load patterns. First, we have just applied the PV loadings, and then we have applied the 50 kilogram per square meter of PV loading in addition to 50 kilogram per square meter of the supporting equipment loading here. So we have a more critical loading scenario here. Here we have observed increase in deflection and increase in number of elements failing under this additional PV panel load in compared to the unloaded structure. In terms of the PV panel load, I'm saying the unloaded structure, only the normal loading. And then we have performed the same analysis for the second loading pattern. and the third loading pattern. It was interesting that in the second loading pattern, when we haven't loaded the central part, in compared to the third loading pattern, we haven't seen we haven't observed many difference. As you can see here, we have 206 elements failing under stress, and with the snow load combination, we have 361 elements failing under the stress. But here, when we fully loading this panel, we again have 361 element loading under this stress. And we also recorded the deflection here and provided the result for the parallel comparison here in the table. So as you can see, here is a normal condition. Here is just adding the load of this PV panel as we have illustrated here. And here, these are the load patterns under the both PV panel plus the installation equipment loads. So this is our most critical case. So when we compare the normal condition under the snow load combination with the additional the ventilation and the dead load of the structure, we had only 315 elements failing under this condition. But when we are coming to our fully loading scenario, fully loading pattern scenario, third loading case, under the same condition, we see that 389 members are failing. Actually, a considerable increase in number of the members failing under the additional load of these PV panels. Even without the installation equipment, we have still 335 members failing, but only a smaller amount of increase in the member failing under this stress. But for sure, we cannot use the existing building, roof and install the panels directly over this, because the member would fail, and we also have experienced 1.5 centimeter additional deflection here. So it's not practical to use the existing aged building as it is and install the photovoltaic panel here. So we recommend to consider the cost of additional roof support as part of the feasibility study, as part of your feasibility study when dealing with the aged buildings having the conventional flat roof. However, it should also be mentioned that this additional support brings other benefit to the project, which usually can justify the additional cost it has, as usually PV panels are constructed with the warranty of 25 years or maintenance period of 25 years. So an aged building without new support structure would cause many problems for both PV panel providers and building occupants. So building the additional support on top of the flat roofs reduce the future maintenance works and in relation to this panel, and also helps us to design this additional steel roof with the optimum angle, so we can achieve the higher efficiency in terms of our PV panel projects. Besides, we can avoid the shadings. Usually, when we want to install this panel, we want to avoid the shading. So this can offer us benefits which would justify the additional cost. This additional supporting roofs cost to our PV panel projects, and it still makes it a feasible project to go, especially considering the 25 years of this project. So a small amounts of efficiency coming from this, even a small amount of efficiency coming from this steel additional roof steel support can do a huge benefit to our project in the long term. So sincerely, this is the end of our presentation, and sincerely I appreciate that I had this opportunity to present to you today. So if you have any question in this regard, please feel free to ask, and I do my best to answer the question. Thank you so much.
Thank you very much for
Thank
your
you.
interesting presentation. I don't see any question from the participants, but I want to ask one question.
Sure, Dr. Hamilton.
I understand, according to the results of your study, you don't suggest to use the existing aged buildings for PV installation, especially for the third load pattern. But you say it will be required to make some additional costs for supporting roof to strengthen the structure. Am I right?
Well, I clarify here that we recommend to install the PV panels over the aged roof, aged buildings actually, and we recommend that it is feasible and beneficial to install it, but with the additional roofing support.
Okay.
For sure, we're gonna have this roofing support.
Mhm.
So we recommend it, but yes, there is an
With
extra
additional
cost of the
stuff.
support.
Mhm. Thank you very much. It is a very nice
Welcome.
topic you share with us. And I think there's another extra questions.
Thank
So
you.
I want to take again, and I will pass to the final presentation of this session. The final presentation will be realized by Doğa Tolgay. And the topic of the presentation is assessment of photovoltaic module temperature estimation for 4 years in Ankara with 4 different software. So I want to also give a short introduction about the speaker. Doğa Tolgay is studying at Middle East Technical University's Physics and Electrical Electronics Engineering Department in a double major program. And Doğa is in the last year now. And Doğa is working in Günam outdoor module test platform since 2017. So I want to invite Doğa for the presentation. Thank you.
Hello. Thank you for this organization. And I think that I have sent it, the video, so maybe you can play it.
Hello, my name is Doğa Tolgay, and today I'm going to present our work, the assessment of photovoltaic module temperature estimation for 4 years in Ankara with 4 different software. In this paper, we try to analyze the temperature estimation formulas developed by 4 softwares by comparing with the module temperatures at the outdoor module test platform. Since the accuracy of the module temperature is an important criteria for software, better temperature estimation will result with better efficiency and better yield estimation. We have analyzed the 4-year data in the cold and semi-arid climate in Ankara. Here is my outline. Today, firstly, I will talk about the Günam and the outdoor model test platform, which then I will talk about the features of the modules that we have used. Then I will talk about the softwares that we have taken our temperature estimation formulas. Then I'll talk about the categories that we have divided our 4-year data into 16 different categories. Then I'll talk about the error calculation. Then I'll mention the outcomes of our work. Then I'll talk about the conclusion of our work. So Günam. Günam is the solar energy research center which is found in Ankara METÜ. It is active from 2009 and it is a multidisciplinary research center which the researchers are from 3 different faculties and 6 different disciplines. Günam has a vision to be a global player, and Günam is also well integrated with the Europe project, with the projects like EU Solaris, Cheetah, and the other 2. Günam has different facilities, various facilities like the Günam photovoltaic line, the GP well, the clean room, the crystal silicon solar cell lab, thin film photovoltaic lab, characterization lab, central laboratory, and the outdoor module test platform. We have made our measurements in the outdoor module test platform while preparing this paper. In the outdoor module test platform is on the rooftop of the Metaphysics building. It contains 16 test beds, which are tilted at 32 degrees angle. These beds are connected to the computer-controlled test platform, which in this platform, we make performance tests, we measure electrical properties, and the subject of this paper, we make temperature measurements. This brings me the features of the modules. We have used 5 different modules. In these modules are the CIS, the monocrystalline silicon, the polycrystalline silicon, micromorph-based amorphous silicon, the HIT, and the CIS module has 130 watts and it is active since October 2014. The monocrystalline silicon module supplies 160 watts and it is active from April 2012. Monocrystalline silicon is active to May 2012 and it supplies 130 watts, whereas the microcrystalline silicon and amorphous silicon tandem structured solar module provides 128 watts and it is active since April 2012. The HIT module provides 230 watts and it is active since April 2012. We have used different temperature estimation formulas that Homer, helioscope, Pvcon, and Pvsol uses these estimation formulas in their yield estimations and efficiency estimations. For the temperature formula, estimation temperature formula used by Homer uses the module parameters such as the efficiency and the temperature coefficients. Whereas the temperature estimation formula used from helioscope uses the empirically determined coefficients like A and B, and also helioscope takes into account of the wind speed also. The estimation formula used by Pvcon is using the efficiency and the empirically determined coefficients and the wind speed also. Whereas the Pvsol uses the only one constant, which is called K, and it only depends on the installation conditions. We have selected these 4 estimation formulas because it is generally used in the industry. So it is a good study to work on them. We have divided our Fourier data into 16 different categories. These categories are divided according to the irradiance and module temperature. From category C1 to C4, the irradiance value is same. However, the ambient temperature value changes. In every 4 category, the irradiance value is same, whereas the ambient temperature value changes. And when you pass from C4 to C5, the irradiance value changes, whereas from C5 to C8, all categories have the same irradiance value, but they have the different ambient temperature values. For C1, the ambient temperature value is below 0, and the irradiance value is between 0 to 300. For all C2, C3, and C4, the irradiance value is the same, but for C2, the ambient temperature is between 0 and 10 degrees. For C3, the ambient temperature is between 10 and 20 degrees, and C4, the ambient temperature is higher than 25 degrees, and the other categories follows also this trend. This brings me the error calculations. The error calculation are done according to the measured temperature minus the estimated temperature, which we have subtracted the estimated temperature from the measured temperature in order to find the error done by the estimation formulas. And after finding this formula, we have calculated the mean absolute error and the root mean square error. We have generated 64 different graph groups, which from 4 different temperature estimation formulas and 16 different categories. In this graph, you can see the only one graph group, which belongs to the category 1 helioscope group. For the category 1 means that it is low irradiance and low temperature category. In these graphs, you can see that the mean absolute error and the root mean square error is low. However, although they are low, the errors can reach up to 20 degrees and minus 10 degrees in the middays. So it is a clue that the model temperature, as the model temperature increases, these temperature estimation formulas are subject to make more mistakes. And similarly, for this graph, you can see the category 4 and PV-SOL group, which the errors made in the middays can reach up to 30 degrees. And it is again a clue that in the middays, the errors done by the temperature estimation formulas are higher. And we think that this is mainly due to the higher module temperatures. In this graph, you can see the temperature estimations done by different temperature estimation formulas according to the categories. In the category 1, you can see the first five formula represents the estimated formulas for category 1. The other subsequent 5 group represents the estimation formulas for category 3, and the other 5 represents the estimation formulas for category 3. And again, I said I think wrongly, this 5 belongs to category 2, and this 5 belongs to category 3. In the CIS module represents by the red line, whereas for the better estimation for monosilicon crystalline module represents by the blue line, and the polycrystalline silicon module is represented by the green line, and the micromorph silicon and amorphous silicon tandem structure module is represented by the gray line, and the magenta line represents the best estimation for the module HIT. In this graph, you can observe that when the irradiance is low, the PV-SOL makes the best estimations. And when the irradiance increases, now the helioscope estimation formula, the estimation formula that helioscope uses becomes to give better results. And you can see that for the tandem structured module like microforce silicon based amorphous silicon, the PV-SOL always makes the best estimations. Independent of the irradiance value and the ambient temperature value, the temperature estimation formula that PV-SOL uses makes the best estimation formulas for the amorphous silicon based, micromorph based amorphous silicon. In the worst estimations, you can see in this graph that the worst estimations for the high irradiance value are done by the temperature estimation formula used by the PV-SOL. Remember that when the irradiance is low, the PV-SOL makes the best estimations. But when irradiance is increased, the temperature estimation formula used by the PV-SOL starts to make the worst approximations. And this brings me the conclusions. I want to again remember that we have made our experiments, our measurements on the cold and semi-arid climate in Ankara. And here are my conclusions. Although mean absolute error and the root mean square error are low, the temperature difference between the measured and the estimated formula are between minus 10 degrees and plus 20 degrees. The temperature difference can reach up to 30 degrees in noon hours. As the ambient temperature increases, the temperature difference also increases. The temperature difference between measured and the estimated formulas are also increases. The Homer, helioscope, and PV-SIST estimations are close to each other. And the PV-SOL can be used, the estimation formula used by the PV-SOL can be used when the irradiance is low. And the estimation formula used by the PV-SOL is not recommended to use when the irradiance is high. and the helioscope do better estimations for mid-range irradiance. So thank you for listening. If you have any questions, I would gladly answer them.
Thank you very much, Doğa, for this presentation. I don't see any question from the participants. Again, I want to ask one question. Did you also make any estimation for the performance or final energy production with these 4 different softwares? Because I just wonder, did you also evaluate what is the performance dependency for temperature for different 5 technologies? Did you make any evaluation about that?
Yeah, it's a nice point. We did not make any research on this, but we are planning to do so because, as you know, these temperature estimations are done in order to calculate the yield and the efficiency estimations. So the main point is that. So we are planning to do this research, and hopefully we will find a good result.
Yeah, because we know from the literature, the different technologies has different dependency for temperature change. So this can be also an interesting topic to add to your research, I think.
Yeah.
Thank you very much.
Thank you.
So there's another question. I don't say another question. So I would like to thank all the speakers for their participation and contribution to this session. And I also want to thank to the participants to be with us during this session. Before I close the session, I want to also make an announcement. The next session, it's session 13, the topic power electronics in PV systems. It will start at 6. So I want to also inform you about that. Thank you very much to all of you. And now I close this session. Thank you.